In chemistry, we expect that breaking a chemical bond requires a specific amount of energy, determined by the bond dissociation energy, BDE, which is calculated based on quantum mechanics and experimental data. Yet in some cases, bonds break far more easily than classical theories predict. How can this happen? And what does it reveal about the hidden complexities of chemical interactions? A surprising example is found in mechanochemistry, where certain bonds, when stretched or twisted, break at much lower energies than expected. Instead of needing the full BDE, mechanical stress can redistribute electron density, making it easier for the bond to dissociate. Imagine pulling apart a zipper. Rather than needing to break every individual link with full force, the whole structure can come undone with much less effort. Another well-documented case involves bond weakening due to quantum tunneling. In hydrogen transfer reactions, for instance, protons sometimes tunnel through activation barriers rather than surmounting them, leading to unexpectedly fast bond dissociation at low temperatures. This effect plays a key role in enzymatic reactions inside biological systems, where quantum effects allow bonds to break efficiently despite mild conditions. Additionally, in solvent-assisted bond breaking, certain polar solvents stabilize charge transition states so effectively that they lower the activation energy required to break a bond. This is particularly striking in water-mediated hydrolysis reactions, where bonds in biomolecules such as DNA and proteins can break much more easily than their gas-phase counterparts. A more exotic example comes from ultrafast laser-induced chemistry. When intense, ultra-short laser pulses hit a molecule, they can create non-thermal electronic excitations that disrupt bonding interactions without needing full thermal energy input. This principle is used in precision laser ablation and could be harnessed for next-generation molecular engineering. Even more puzzling, in some cases, bonds appear to self-weaken due to collective electronic effects. In metal ligand coordination complexes, for instance, adding or removing electrons can dramatically weaken specific bonds, enabling reactions to proceed under unexpectedly mild conditions. Why does adding a tiny charge change the entire bond structure? The answer lies in the complex, many-bodied interactions between electrons, which classical theories struggle to fully describe. The Bond Strength Anomaly paradox challenges our traditional understanding of molecular stability and reaction dynamics. If bonds can break at much lower energies than expected, could there be hidden reaction pathways in biochemistry and materials science that we have yet to uncover? This paradox isn't just a curiosity. It has profound implications for fields like catalysis, nanotechnology, and even the development of advanced pharmaceuticals. Are we underestimating how fragile some chemical bonds truly are? By investigating these anomalies, scientists may unlock new ways to control chemical processes with unprecedented precision. Chemical bonds are traditionally understood to break when supplied with energy equal to or greater than their bond dissociation energy, BDEE. However, experimental evidence suggests that in certain conditions, such as nanoscale confinement, quantum effects, or catalytic environments, bonds can rupture at significantly lower energy levels. This paradox challenges classical chemistry and implies that hidden interactions, non-thermal activation mechanisms, or quantum fluctuations play a role in bond weakening. Hydrogen bonds in enzymatic reactions often break at much lower energies than predicted by simple thermodynamic models, enabling high-efficiency biological catalysis. This is like a rope snapping in under a much smaller force when tension is applied in a precise manner rather than through brute force. Quantum mechanical tunneling allows particles to overcome energy barriers without requiring classical activation energy. In bond dissociation, light atoms such as hydrogen exhibit tunneling effects, allowing their bonds to break at energies well below the expected threshold. This process is particularly significant in low-temperature chemistry and enzyme catalysis, where quantum effects enable reactions that would otherwise be thermally inaccessible. In biochemical reactions, tunneling of protons in hydrogen bonds reduces the energy needed for DNA mutation processes, influencing genetic stability. This is like a person slipping through a gap in a fence instead of climbing over it, bypassing the need for extra energy. At the nanoscale, molecular interactions are modified by spatial constraints, altering electron distributions and bond strengths. Confinement effects can lead to localized strain, polarization, or hybridization, reducing the effective energy required to break a bond. These effects are particularly pronounced in nanocatalysts, where reaction kinetics deviate from bulk material behavior. In carbon nanotube systems, confined molecular interactions lead to bond dissociation energies significantly lower than in free molecules, accelerating reactions. This is like a metal spring losing tension when compressed inside a tight space, making it easier to break. Catalysts lower activation energy by providing alternative reaction pathways, but certain catalytic processes break bonds at energies much lower than expected. This anomaly arises from complex electronic effects, including charge transfer, surface polarization, and transition state stabilization, which weaken bond strength. These mechanisms play a crucial role in industrial catalysis and sustainable energy applications. In hydrogen fuel cells, platinum catalysts facilitate hydrogen bond cleavage at far lower energies than the intrinsic BDE of H2 molecules. This is like using a lever to lift a heavy object with minimal effort, redirecting force to achieve the same result more efficiently. Molecular vibrations influence bond stability, and selective excitation of specific vibrational modes can lead to rapid bond dissociation at lower than expected energies. When energy is funneled into critical vibrational states, bonds may rupture without requiring full thermal activation. This process is particularly relevant in femtosecond laser chemistry, where targeted energy deposition enables ultrafast bond cleavage. Infrared-driven dissociation of methane, CH4, occurs at lower energy inputs when vibrational resonances are exploited. This is like finding the perfect rhythm to break a tree branch with minimal force. Applying energy in the right way reduces effort. In some molecular systems, electron delocalization leads to bond weakening due to charge redistribution effects. When bonding electrons become shared over a larger molecular framework, individual bond strengths decrease, making breakage easier. This is particularly evident in conjugated organic molecules and transition metal complexes. In graphene and fullerenes, bond dissociation is influenced by p-electron delocalization, leading to anomalous mechanical properties. This is like stretching a net. When tension is spread across multiple points, any single strand becomes easier to snap. High electric fields can destabilize chemical bonds by inducing charge separation and polarizing electron density. This effect reduces bond strength and can lead to field-assisted bond cleavage at significantly lower energy inputs. Such phenomena are critical in atmospheric chemistry, plasma reactions, and molecular electronics. In lightning-induced reactions, atmospheric nitrogen bonds break at energies much lower than predicted due to extreme electrostatic effects. This is like pulling apart a magnetized object. When charge distribution is altered, the binding force weakens. Some reactions occur via non-thermal activation, where bonds break due to electronic excitation, photon absorption, or mechanical force rather than heat. These processes allow chemical transformations in cold environments, challenging classical energy barrier models. Such effects are important in astrochemistry, where molecules form and break in extreme low-temperature conditions. In interstellar clouds, UV photons trigger the dissociation of water and organic molecules without significant thermal energy input. This is like cracking an ice cube by hitting a precise weak point instead of waiting for it to melt. The unexpected weakening of chemical bonds under specific conditions challenges our understanding of reaction kinetics and material stability. Investigating these anomalies helps improve catalysts, designed stronger yet more reactive materials, and refined theoretical models of chemical bonding. Future advancements may lead to breakthroughs in drug design, energy storage, and quantum chemistry. In molecular electronics, controlled bond weakening is used to design self-healing materials and adaptive electronic circuits. This is like engineering a bridge that can flex under pressure instead of breaking, enhancing resilience while maintaining strength.